When you drop a stone into a pond and watch the ripples spread outward, it feels like one of the simplest and most natural things in the world. The stone falls because of gravity. It is such an old and familiar word that most people never stop to question it. We feel it in every step we take, in the pull of our bodies toward the ground, in the way oceans swell and retreat in tides, and in the fall of rain from clouds above. Yet behind that simplicity lies one of the deepest mysteries in all of science. Long before the modern era of physics, people wondered why objects fall. Aristotle believed that things seek their natural place. Heavy objects belong to the earth, light objects belong to the heavens, and so the stone falls while fire rises. That explanation satisfied generations until a very different thinker, Isaac Newton, asked sharper questions. In the year 1687, he published his Principia Mathematica, laying out a universal law of gravitation. He claimed that every mass attracts every other mass in the universe, with a force that depends on the product of their masses and decreases with the square of the distance between them. For the first time, the same principle explained why an apple falls from a tree and why the moon orbits the earth. Newton's insight was revolutionary because it united heaven and earth under a single rule. The apple and the moon were not governed by separate laws. They were joined by the same invisible pull. With careful mathematics, Newton could predict the paths of planets, the return of comets, and the orbits of moons. His equations became a triumph of human thought, and for more than 200 years they ruled physics. But even Newton admitted he did not know what gravity was. He had found a law to describe its strength, but he offered no mechanism. What invisible hand reached across space to pull bodies together? He wrote, "I frame no hypotheses." To him, gravity was a given fact of nature, measurable but unexplained. That mystery lingered until the early 20th century, when another mind dared to rethink the universe itself. Albert Einstein was troubled by Newton's picture of forces acting instantly across empty space. Working with the strange insights of special relativity, which insisted that nothing travels faster than light, Einstein began to wonder if gravity could be reimagined, not as a force, but as a feature of geometry. In 1915, he unveiled the general theory of relativity. According to Einstein, matter tells space how to curve, and curved space tells matter how to move. Gravity was not a mysterious tug, but the warping of space-time itself. Imagine placing a heavy ball on a rubber sheet. The sheet dips, and a smaller ball placed nearby will roll inward, not because it is pulled by some invisible string, but because the sheet itself guides its path. In the same way, Earth moves around the Sun because the Sun curves space-time, creating the geometry in which planets follow nearly circular orbits. Einstein's equations of general relativity were not just elegant. They predicted new effects, like the bending of light around stars and the slowing of time near massive objects. Within a few years, experiments confirmed these predictions, and Newton's once absolute theory gave way to Einstein's deeper vision. Relativity explains nearly everything we see on the grand cosmic stage. It describes the dance of galaxies, the collapse of stars into black holes, and even the expansion of the universe itself. Yet, despite its power, relativity stands strangely apart from another pillar of physics, quantum mechanics. The quantum world governs atoms and subatomic particles with rules that are probabilistic, statistical, and strange. When physicists try to merge relativity with quantum mechanics, contradictions arise. Gravity, so familiar and so overwhelming in daily life, becomes elusive at the smallest scales. Unlike electromagnetism or the nuclear forces, gravity resists quantization. Attempts to force Einstein's theory into the quantum mold often lead to infinities or paradoxes. Physicists have built quantum field theories that explain electrons, quarks, and photons with astonishing accuracy, but gravity remains stubbornly outside the fold. This is the paradox at the heart of modern physics. On the largest scales, gravity reigns supreme, shaping the fate of stars and galaxies. On the smallest scales, where quantum rules hold sway, gravity seems almost absent, too weak to measure, too difficult to tame mathematically. The two great frameworks of physics refuse to merge. One describes the very large, the other the very small, but between them lies a rift. For more than a century, this gap has haunted physicists. Some believe that a theory of quantum gravity must exist, waiting to be discovered, perhaps involving hypothetical particles called gravitons. Others suspect that gravity is not fundamental at all. Perhaps it is not a force written into the fabric of reality, but an emergent phenomenon, like temperature or pressure, arising from deeper, microscopic laws. The stone that falls into the pond, the moon that circles the Earth, the galaxies bound together across millions of light years, all these may not be pulled by some fundamental interaction. They may be illusions born from hidden layers of physics. If that is true, then gravity is not what it seems, and the mystery is even deeper than Newton or Einstein imagined. To see if gravity is truly an illusion, we must first understand the other side of the story, the strange world of quantum mechanics, where probability replaces certainty and particles can be waves at the same time. Only by comparing these two realms can we ask whether gravity is a fundamental force of nature or a shadow cast by the quantum world. The universe is filled with motions so steady and predictable that they once seemed to prove gravity was the most trustworthy of laws. Planets rise and set with clockwork precision, tides return with the rhythm of the moon, and eclipses can be foretold centuries in advance. To the human eye, nothing could appear more certain. Yet the deeper scientists look, the more gravity begins to slip away from certainty and into mystery. The law that once united the heavens and the earth now appears incomplete, as though it were only a chapter in a book whose ending we have not yet read. Einstein's general relativity did more than bend space and time. It revealed a universe where gravity is not a force acting in the background, but a property of the stage itself. Space and time are not passive containers. They are dynamic, stretching and curving in response to matter and energy. This revelation stunned the scientific world, but it also raised new puzzles. If space-time can bend, can it also ripple? Einstein's theory said yes, predicting waves of curvature racing through the cosmos at the speed of light. These gravitational waves remained a theoretical dream for a century until, in 2015, the LIGO Observatory announced their detection. Black holes, spiraling together and colliding, had shaken the very fabric of space and time, and sensitive instruments on Earth had felt their whisper. This triumph of relativity made the mystery sharper, not smaller. Detecting gravitational waves confirmed Einstein's vision at cosmic scales. But could such ripples also be explained in quantum terms? When scientists tried to apply the mathematics of quantum mechanics to these vast distortions, the equations refused to cooperate. In quantum theory, every force has a carrier particle. Electromagnetism has photons, the strong nuclear force has gluons, the weak force has W and Z bosons. If gravity is also a force, then it too should have a quantum messenger. Physicists call this hypothetical particle the graviton, yet no experiment has ever seen one. The absence of gravitons is not surprising. Gravity is immensely weaker than the other forces. Two magnets can lift a nail against the entire pull of the Earth. To detect a single graviton, an instrument would need to be larger than the planet itself and sensitive beyond imagination. In practice, such a search may be forever impossible. That leaves physicists in a strange position. They can write equations for gravitons, and these equations behave consistently in limited contexts, but they cannot prove that such particles exist. This is where the suspicion grows that gravity might not be fundamental. If a particle cannot be observed, even in principle, perhaps it is not real in the way photons or electrons are real. Instead, gravity may be an emergent effect, like the smooth surface of water emerging from countless molecules in motion. In that view, space-time itself may be a large-scale illusion, a projection of deeper, quantum degrees of freedom. The idea seems radical, but history reminds us that radical shifts are not rare in science. Once heat was considered an invisible fluid called caloric. Only later did physicists discover that heat is the collective motion of atoms. Once life was thought to be governed by a vital force beyond chemistry. Now biology is understood as the emergent result of molecular interactions. If gravity turns out to be another emergent phenomenon, it would follow a familiar pattern. What seems fundamental at one scale is revealed as secondary when we peer deeper. Yet before we can weigh this possibility, we must explore the nature of the quantum world itself. For gravity to be emergent, it must somehow arise from quantum rules, and those rules are stranger than any picture offered by Newton or Einstein. They involve particles that behave like waves, events that are uncertain until measured, and connections that stretch across space in ways that defy ordinary logic. Compared with this quantum strangeness, the pull of gravity may be the illusion, the ordinary effect masking a deeper stratum of reality. Einstein himself was never fully comfortable with the indeterminacy of quantum mechanics. He famously declared that God does not play dice. Yet, experiment after experiment proved him wrong. At the smallest scales, nature is probabilistic. The position of an electron, the decay of an atom, the polarization of a photon, all obey rules of chance rather than certainty. Despite this, quantum theory is not vague, it is precise, predicting the outcomes of experiments with incredible accuracy. It underlies modern electronics, lasers, and nuclear energy. The paradox is that while quantum mechanics works, it remains incomplete. It has no natural place for gravity. So we face two towering frameworks. Relativity governs the cosmos, explaining black holes and galaxies. Quantum mechanics governs the microscopic, explaining atoms and particles. Both are correct in their domains, yet they clash at the boundary where the very small and the very massive meet. Near the center of a black hole, or at the beginning of the universe, the equations of relativity and quantum mechanics both demand to be heard, but they speak different languages. This is the heart of the mystery. The next step in our journey must therefore lead us into the quantum world itself. Only by entering that strange domain can we judge whether gravity is a fundamental actor in the play of reality, or only a shadow cast upon the stage by deeper quantum laws. The story of gravity is as much about human imagination as it is about the cosmos itself. To call something a force, to assign it equations and symbols, is already to take a leap of faith. Newton leapt by proposing a universal attraction. Einstein leapt further by reshaping space and time. Now physicists stand at the edge of another leap, wondering whether the very concept of gravity is misleading us, whether it is not a true building block of reality, but a mirage created by deeper structures. To appreciate the weight of this question, we must remind ourselves of how deeply gravity is woven into human life. Every breath we take depends on it. Our atmosphere clings to the Earth because gravity holds it close. Without that pull, the air would escape into space, and our world would be barren. The oceans rise and fall not only with the moon's pull, but with the subtle influence of the sun, their dance carving shorelines and shaping ecosystems. Our muscles and bones grew strong under its pressure. Astronauts who spend months in orbit return weaker, their bodies reminding us how accustomed we are to gravity's constant embrace. It is no wonder that to us, gravity feels more real than any other force. We can walk past magnets or electric fields without noticing them, but gravity never lets us go. Yet this familiarity is deceptive. When we attempt to merge the equations of gravity with quantum mechanics, infinities explode out of the mathematics. Calculations that should yield sensible numbers instead diverge into nonsense. To tame these infinities, physicists have tried many approaches, from string theory to loop quantum gravity. String theory replaces particles with vibrating strings of energy, hoping that gravity emerges as one of their harmonics. Loop quantum gravity imagines space itself as woven from discrete loops, tiny quanta of geometry that build space-time piece by piece. Both are ambitious, both elegant in different ways, and both remain unproven. Meanwhile, experiments continue to probe the boundaries. Sensitive instruments measure the pull of gravity at millimeter scales, searching for deviations that might hint at hidden dimensions or new physics. So far, Newton's and Einstein's predictions still hold. Observatories scan the sky for clues in the motions of galaxies, which rotate in ways that suggest unseen mass, a mystery called dark matter. Some physicists argue that dark matter is real, made of invisible particles yet to be discovered. Others suggest that perhaps gravity itself behaves differently on galactic scales, an emergent illusion that mimics the presence of unseen matter. The debate is fierce because evidence is scarce and interpretations are many. Yet at its core, the mystery remains the same as it was for Newton. We can measure how gravity behaves. We can predict its effects with extraordinary accuracy. But what is it really? A fundamental force with its own particle, like the photon of electromagnetism, or a large-scale appearance of quantum processes that we do not yet understand? This uncertainty is what makes the study of gravity so profound. It forces us to confront the limits of knowledge. It reminds us that even the most familiar truths may be provisional, awaiting deeper explanation. We have gone from apples falling in orchards to black holes colliding across billions of light years, and still, the essence of gravity eludes us. The next chapters will carry us into the strange realm of quantum mechanics, where certainty dissolves and probability rules. It is there, in the interplay between the quantum and the cosmic, that we may begin to glimpse whether gravity is a fundamental actor in the universe, or a remarkable illusion born of quantum information. And so the mystery deepens. We stand between Newton's apple and Einstein's curved spacetime, between the certainty of falling stones and the uncertainty of quantum particles, unsure whether gravity is the deepest truth or the most convincing illusion. To unravel this paradox, we must leave the comfort of the familiar and enter the quantum puzzle. At first glance, the world of the very small does not seem to obey any rules at all. Electrons leap unpredictably from one orbit to another. Light behaves as both particle and wave. A particle can be in two places at once, and only when we measure it does it seem to choose. To classical thinkers, this was absurd. To modern physics, it is the foundation of everything. The strange mathematics that grew from these puzzles in the early 20th century became quantum mechanics, a framework that explains the atom, the structure of matter, and the forces that govern them with a precision no other theory can match. The journey began with hints that the old view of nature was incomplete. At the dawn of the 20th century, physicists studying radiation from hot objects discovered that their equations broke down. Classical physics predicted infinite energy pouring from a black body radiator, an absurdity known as the ultraviolet catastrophe. Max Planck resolved the crisis by proposing that energy is not continuous but comes in discrete packets called quanta. This was a radical idea. A few years later, Albert Einstein applied the same notion to light, explaining the photoelectric effect by treating light as particles of energy, later called photons. From there, the quantum story unfolded with increasing strangeness. Niels Bohr showed that electrons orbit atoms not in any path they please, but in discrete shells, jumping between them only by absorbing or releasing photons. Louis de Broglie suggested that particles themselves act like waves, and experiments soon confirmed that electrons can interfere like ripples on water. Werner Heisenberg formalized the uncertainty principle, which states that certain pairs of properties, like position and momentum, can never both be known exactly. Erwin Schrödinger wrote equations describing particles as wave functions, clouds of probability, rather than definite points. Each step chipped away at the comfortable picture of a deterministic universe. Instead of exact outcomes, quantum mechanics offered only probabilities. An atom might decay within a second or within an hour, and the best physics could do was give the odds. Yet the power of these odds is astonishing. Quantum mechanics predicts the structure of the periodic table, the spectra of stars, the behavior of semiconductors and superconductors. It is the reason computers, lasers, and nuclear power exist. It is not a vague or speculative theory. It is the most tested and confirmed framework in all of science. But success raises a new question. If quantum mechanics explains electromagnetism through photons, and if it explains the strong nuclear force through gluons, and the weak nuclear force through W and Z bosons, what of gravity? If every force is carried by a quantum particle, where is the graviton? Here lies the puzzle. Gravity refuses to fit. One way to see the difference is in strength. The electromagnetic force between two protons is about 10 to the power of 36 times stronger than their gravitational attraction. On the atomic scale, gravity is negligible. It has no role in chemical bonds, nuclear reactions, or particle physics. Only when enormous amounts of mass are involved does gravity become significant. This makes it invisible in the laboratory of the quantum world. And yet, paradoxically, on the largest scales, gravity dominates everything. Stars burn, galaxies form, black holes devour matter. The universe itself expands all under gravity's control. Thus, physics is split. Quantum mechanics governs the small with unimaginable precision. Relativity governs the large with majestic power. Neither can replace the other, and both collapse when forced together. Physicists have tried to bridge the gap with quantum field theory, which treats forces as excitations of underlying fields. Quantum electrodynamics describes electrons and photons interacting through a shimmering electromagnetic field, and its predictions agree with experiments to an accuracy of 1 part in a trillion. Quantum chromodynamics describes quarks bound by gluons, explaining the nuclei of atoms. These field theories are among the greatest triumphs of science, but gravity refuses to join them. Attempts to quantize Einstein's curved spacetime lead to nonsensical infinities that no clever trick can cancel. Some argue that this is not a flaw of mathematics but a clue about reality. Maybe gravity is not a force in the same sense as electromagnetism or the nuclear forces. Maybe it emerges from something deeper, something purely quantum, so that trying to assign it a particle is like trying to describe waves with individual droplets of water. The graviton, if it exists, may not be a fundamental building block, but a convenient illusion. This possibility unsettles and excites physicists in equal measure. On one hand, It threatens to unravel a century of assumptions about unification, the dream that all forces can be explained by a single framework. On the other hand, it hints at a deeper unity where gravity is not an outsider but a collective effect of quantum information. The puzzle is not just theoretical, it shows up in practical paradoxes. What happens at the center of a black hole, where mass collapses to a singularity and relativity predicts infinite curvature? What happened in the first instant of the universe, when all matter was compressed into a point smaller than an atom? In both cases, relativity alone fails. Quantum mechanics alone also fails. Only a union could explain these extremes. And so, physics waits at a crossroads. We know gravity cannot be ignored, and we know quantum theory cannot be wrong, but we cannot make them agree. That is why some scientists whisper that perhaps there is nothing to quantize, no graviton to find. Perhaps gravity is the shadow, not the substance. The next step in the story leads directly into this possibility. If gravity does have a particle, then it is fundamental. If no such particle exists, then perhaps we must accept that gravity is emergent, born from deeper principles of information and entropy. The search for this elusive graviton is more than a quest for a particle. It is a test of whether reality is built the way we think it is, or whether the universe is far stranger than we dare imagine. The strange success of quantum mechanics lies in its ability to predict events that no one could have imagined without it. If you fire a stream of electrons at a barrier with two slits, each electron seems to pass through both slits at once, interfering with itself and creating a wave pattern on the screen behind. Only when you measure which slit it goes through does it behave like a single particle. The experiment is so well known that it has become a symbol of the quantum world. It reveals that particles are not little billiard balls, but clouds of probability that collapse into definite states only when observed. This duality between particle and wave is not just a curiosity. It is the foundation of chemistry and biology, of the binding of atoms and the folding of proteins. Every heartbeat, every thought in the human brain is powered by quantum effects at the scale of molecules. And yet gravity is absent from this story. You can repeat the double-slit experiment 1,000 times, and gravity plays no role in the outcome. It is as though the universe has two sets of rules that do not speak to each other. Physicists have long dreamed of unification. James Clerk Maxwell showed that electricity and magnetism are two aspects of the same force. Later, scientists discovered that the weak nuclear force is also connected to electromagnetism, forming what we call the electroweak force. These triumphs of unification encourage the hope that all forces might eventually be understood as one. But when gravity is invited to join, it resists, as though it belongs to a different story. Why is gravity so difficult to fit into quantum language? Part of the answer is its weakness. The gravitational pull between two elementary particles is so faint that it is drowned out by every other interaction. In practice, no particle collider on Earth could hope to measure it. Even the mighty Large Hadron Collider, smashing protons together at near the speed of light, is blind to gravity's quantum effects. The only time gravity's strength rivals other forces is at scales so extreme that they defy experiment, such as inside black holes or at the birth of the universe. Another part of the answer is conceptual. Quantum mechanics thrives on uncertainty and fluctuation. It describes particles popping in and out of existence in quantum fields, borrowing energy for brief moments in accordance with the uncertainty principle. But relativity describes space-time as smooth and continuous, bending under the weight of matter and energy. When quantum fluctuations are applied to space-time itself, the smooth fabric tears into a foamy chaos at the smallest scales, and the equations lose meaning. It is as if two musical instruments, each perfectly tuned, produce only noise when played together. Still, physicists press on. Some imagine that space-time itself must be quantized, made of indivisible units like the pixels of a screen. Others imagine that new dimensions of space hide from our perception, rolled up so tightly that we cannot see them, yet shaping gravity's behavior in ways we do not expect. These ideas may sound exotic, but they arise from the stubborn refusal of the known theories to unite. If reality is consistent, there must be a deeper explanation, and many believe that explanation will show us whether gravity is a true force or an emergent illusion. The search for gravitons, the hypothetical particles of gravity, represents this tension. If we find them, gravity takes its place alongside the other forces in the quantum family. If we do not, then perhaps we must change the question entirely. Perhaps there is no particle to find because gravity is not a fundamental interaction but a macroscopic effect, a byproduct of quantum entanglement and information. The possibility is unsettling because it means that the force we experience most directly may not be written into the fabric of the universe at all. Quantum mechanics forces us to be humble. It teaches that what seems obvious may be false, that certainty is an illusion, and that reality is built from probabilities. Gravity may be subject to the same lesson. What seems like the most real and constant of forces may be only the large-scale shadow of something else, just as temperature is the large-scale shadow of atomic motion. The truth, however strange, must lie where quantum and gravity meet, in a realm we have only begun to explore. This brings us to the critical question: can we ever test whether gravity has a particle? Can we detect the graviton, or prove that it does not exist? The next part of the story leads us directly into this search, a quest that may decide whether gravity is fundamental or an illusion born of quantum laws. The dream of finding a quantum particle for gravity has inspired generations of physicists, but the obstacles are immense. To understand why, imagine what it would take to detect a single graviton. Gravitons, if they exist, would interact with matter so faintly that even a detector the size of Jupiter would have little chance of recording one event in the lifetime of the universe. The weakness of the signal is not a flaw of engineering, but a fundamental fact about gravity itself. Unlike photons or electrons, which can be measured and manipulated in laboratories, gravitons remain forever beyond direct reach. This impossibility forces physicists into indirect approaches. Instead of hunting for single gravitons, they study the collective behavior of gravity in extreme environments. They analyze the ripples of space-time produced by colliding black holes. They measure the bending of light around galaxies. They compare the cosmic microwave background, the faint afterglow of the Big Bang, against predictions of quantum models. In each case, they hope for a fingerprint that reveals gravity's true nature. So far, relativity's classical picture continues to hold. No deviations, no cracks, no hidden signatures of quantum behavior. Yet the absence of evidence does not mean the end of the quest. It may mean that we are asking the wrong question. If gravity is emergent, then expecting to find a graviton is like expecting to find a single particle of heat. Heat is not a fundamental entity, but the average motion of molecules. In the same way, gravity might be a large-scale effect of quantum information, a pattern that emerges only when many microscopic interactions combine. The graviton would then be an illusion, a useful fiction in some equations, but not a real piece of the universe. This possibility is controversial. Many physicists resist the idea because it threatens the cherished dream of unification. They want all forces described by the same framework, with each force having its own particle. The search for the graviton embodies this dream. Without it, gravity remains the outsider, the stubborn rule that refuses to play by the quantum script. But history reminds us that science often advances by abandoning assumptions. If the graviton is never found, perhaps it is because it was never there to begin with, and so the quantum puzzle deepens. Gravity may be the missing piece in the quantum mosaic, or it may be a mirage created by the mosaic itself. The only way forward is to keep testing, to push experiments to the limits, to probe the cosmos for signs that either confirm or deny gravity's place as a fundamental force. Until then, we live with uncertainty, caught between two grand theories that cannot be reconciled. The next chapter will turn directly to this search for gravitons. We will ask what they are supposed to be, why they are so hard to detect, and what it would mean if they do not exist at all. For in the fate of the graviton lies the answer to one of the deepest questions of all. Is gravity truly fundamental, or is it the most convincing illusion the universe has ever shown us? Physicists are dreamers, but they are also builders. They dream of grand unifications, but they also build experiments to test them. The graviton is perhaps the most elusive dream of all. In theory, it should exist if gravity is truly a quantum force. Just as photons carry the electromagnetic force, the graviton would carry the force of gravity. It would be massless, traveling at the speed of light, and it would interact with everything that has mass or energy. If we could prove its existence, gravity would finally join the other forces in the quantum family. But proving that existence is another matter. The problem begins with gravity's weakness. Imagine two electrons repelling each other electrically. The force is colossal compared with their gravitational pull. In fact, the electromagnetic force between two electrons is stronger by a factor of 10 to the power of 40. This disparity means that in the world of atoms, molecules, and particles, gravity is negligible. It is drowned out by other forces so completely that we can ignore it in almost every quantum calculation. Only when we gather astronomical masses does gravity matter, and by then the quantum effects are far too small to detect. The graviton, if it exists, is hidden in a veil of weakness. Still, physicists try to pin it down with mathematics. In quantum field theory, forces are described as exchanges of particles. An electron emits a photon, another electron absorbs it, and the result is electromagnetic repulsion. By analogy, two masses would exchange a graviton, and the result would be gravitational attraction. The idea fits beautifully into the framework of particle physics, and calculations using virtual gravitons can even mimic Einstein's predictions in limited ways. But when the mathematics is pushed too far, contradictions appear. The equations spiral into infinities that no renormalization trick can tame. Unlike photons or gluons, gravitons refuse to play nicely in the quantum sandbox. The practical obstacles are even worse. To detect a photon, you only need a small sensor. To detect a graviton, you would need an apparatus larger than planets and more sensitive than any conceivable technology. Gravitons would pass through matter almost without interacting. Even if a graviton brushed against your body, you would never feel it, and no instrument could register it. This has led many to declare the direct detection of gravitons impossible in principle, not just in practice. If so, then the graviton may forever remain a ghost in our equations, never to be caught in reality. Some argue that we do not need to catch a graviton directly to prove its existence. Instead, we can search for indirect signs. For example, in the faint afterglow of the Big Bang, known as the cosmic microwave background, there may be imprints of primordial gravitational waves. If those waves show specific quantum patterns, they could serve as indirect evidence of gravitons. Similarly, careful studies of black hole radiation might reveal subtle quantum features pointing to graviton behavior. These methods are speculative, but they represent the only hope for evidence. The stakes are high. If gravitons are ever confirmed, it would cement gravity as a fundamental force, not an emergent illusion. It would prove that space-time itself can be quantized, woven from discrete threads of interaction, like every other field. But if gravitons never appear, even indirectly, then we must consider that our picture of gravity is wrong. Perhaps space-time is not a field to be quantized, but a large-scale pattern that emerges from something deeper. The graviton would then be like the caloric fluid once imagined to explain heat, a useful fiction discarded when deeper knowledge arrived. For now, physicists remain divided. Some continue to search for gravitons with optimism, convinced that nature must be consistent and that no force can resist quantization. Others see the endless failures as a sign that gravity is different, that it belongs to another layer of reality altogether. Both camps agree on one thing: solving this mystery will transform our understanding of the universe. The search for gravitons is not just about particles. It is about whether gravity is real in the way we think it is, or whether it is the greatest illusion of all. The answer, whichever way it falls, will reshape the very foundations of physics. The question of detecting a graviton is often asked by students and researchers alike, and the answer is always the same. It is hopeless with present or even foreseeable technology. To understand why, we must compare the scale of forces. A photon can trigger the response of a single atom in a detector, releasing an electron and producing a measurable signal. A graviton, by contrast, would glide past nearly all matter as though it were transparent. It would couple so weakly to any detector that the odds of catching one are essentially zero. Even if you built a detector the size of the Earth, waiting for 10 to the power of 20 years, the chance of recording a graviton event would still be vanishingly small. This has not stopped physicists from imagining clever ways to test for its existence indirectly. Some proposals involve looking at gravitational waves. These are ripples in space-time, predicted by Einstein and confirmed a century later. If we could examine those waves with infinite precision, we might see signs that they are composed of individual quanta, like how a beam of light is composed of photons. But our detectors, vast as they are, cannot yet separate such fine details. Gravitational waves wash over our planet with amplitudes smaller than a proton, and even detecting them at all required technology of breathtaking sensitivity. To resolve their quantum grain is far beyond what we can do. Another idea is to search the cosmic microwave background for patterns left over from the earliest universe. In its first moments, the cosmos may have been filled with violent quantum fluctuations that generated gravitational waves. Those waves, in turn, may have imprinted a subtle swirl in the polarization of the background light. If we find such a signal, it could be evidence of gravitons. Several experiments have hunted for this pattern, and though there have been tantalizing hints, nothing conclusive has appeared. The sky continues to guard its secrets. Physicists also consider the radiation from black holes as a possible window. Stephen Hawking showed that black holes are not entirely black, but emit faint radiation due to quantum effects near the event horizon. If this radiation can be studied in detail, perhaps it could reveal features tied to gravitons. But again, the challenge is overwhelming. Hawking radiation is unimaginably faint, far below the sensitivity of any telescope. Detecting it directly would require waiting longer than the current age of the universe. All of this leads many to believe that the graviton may be undetectable, not just practically but fundamentally, and here the debate deepens. Some argue that if a particle cannot be detected even in principle, it does not deserve to be called real. Others reply that theoretical consistency alone is enough reason to believe in its existence. After all, the graviton fits neatly into the quantum field picture, and discarding it may leave gravity without a proper description. This debate cuts to the philosophy of science itself. What does it mean for something to exist? Must it be observable, or is mathematical necessity enough? Physics has faced this question before. Atoms were once invisible, debated for centuries before experiments proved their reality. Neutrinos were proposed as invisible particles to save the conservation of energy in nuclear decay. For years, they were only a mathematical ghost, until experiments finally confirmed them. Perhaps gravitons will follow the same path, their discovery postponed by the sheer difficulty of the task. Yet there is a difference. Unlike atoms or neutrinos, the graviton may forever escape detection by its very nature. That possibility makes it unique in physics, straddling the line between theory and philosophy. If it is never observed, we may have to accept that gravity does not belong to the same family as other forces, that it is not carried by a particle, but arises from another principle altogether. The debate does not weaken the mystery, it sharpens it. If gravitons exist, they will unify gravity with quantum mechanics and complete the picture. If they do not, then gravity must be emergent, a phenomenon built from something deeper. Either way, the search reveals the edges of our knowledge, the places where physics itself begins to blur into the unknown. The next part of the journey will explore this possibility more deeply, asking whether gravity could be a projection, a hologram, or an emergent feature of quantum information. If the graviton remains forever absent, perhaps the reason is that we have been looking for something that does not exist. The graviton stands as a dividing line between two visions of the universe. On one side lies the belief that gravity is fundamental, just like electromagnetism and the nuclear forces. In this vision, reality is composed of quantum fields, and every force is mediated by a particle. The graviton, though unseen, is as real as the photon, the gluon, or the W and Z bosons. Its existence is a matter of consistency, not convenience. Without it, the framework of particle physics feels incomplete. On the other side lies the idea that gravity is not fundamental at all, that it emerges from deeper principles. If this is true, then the graviton is not missing, it is unnecessary. To imagine an emergent gravity, think of temperature. No one molecule in a glass of water has a temperature. Temperature exists only when countless molecules move together in chaotic motion. It is a large-scale property, an illusion born of statistics, though no less real for being emergent. In the same way, gravity may be a property of space-time that emerges from the quantum entanglement of countless particles. If so, the graviton is like the mythical caloric fluid once believed to carry heat, a ghost of old theories that eventually gave way to deeper truths. This is where the search for gravitons transforms from physics into philosophy. If we never observe a graviton, how do we decide whether gravity is fundamental or emergent? Do we hold on to the particle picture, trusting in the success of quantum field theory, or do we abandon it, opening the door to radical new ideas like holographic universes and entropic forces? The choice is not merely technical, it is a choice about how we think the universe works at its core. Physicists are cautious. Many still expect gravitons to be real, even if forever beyond reach. The elegance of unification is too compelling to abandon easily, yet others are bold enough to let go of the dream. They point to the mounting evidence that gravity behaves differently from the other forces, and to the conceptual roadblocks that have resisted resolution for more than a century. To them, the graviton is not an answer, but a distraction. Whichever path turns out to be true, the consequences are profound. If gravitons exist, they will anchor gravity firmly within quantum theory, and perhaps one day allow us to build a full quantum theory of spacetime. If gravitons do not exist, then we must accept that the universe plays by deeper rules, rules in which gravity is not a player, but a shadow, a pattern, a large-scale illusion born of quantum information. Either outcome will transform physics, and so the search continues, not in laboratories alone, but in the minds of theorists, in the equations written on chalkboards, and in the dreams of unification that have guided science for centuries. The graviton remains hidden, a ghost particle at the edge of thought. To find it would be to prove that gravity belongs to the same family as the other forces. To fail to find it may be to discover that gravity is not a force at all, but the grandest illusion of the cosmos. Our journey now leads to a new idea, one that shifts the very foundation of perspective. What if spacetime itself is not fundamental? What if everything we see, including gravity, is a projection from a deeper reality? This is the startling suggestion of the holographic principle, a concept born from the study of black holes. It is there, in the mathematics of entropy and horizons, that the next clues await. Imagine holding a hologram in your hand. At first glance, it looks like an ordinary flat sheet of plastic or glass. But when light strikes it from the right angle, a three-dimensional image shimmers into view. Tilt it, and the perspective changes, as if the object were really there. Yet the image is an illusion. The information needed to create the three-dimensional scene is entirely encoded on the two-dimensional surface. What you see is a projection, a trick of physics and light. This simple analogy has become one of the most audacious proposals in modern theoretical physics, the holographic principle. The holographic principle suggests that everything we experience as three-dimensional space may itself be a projection of information stored on a lower dimensional boundary. If this is true, then spacetime, and with it, gravity, is not fundamental, but emergent. We may be living inside a cosmic hologram where the pull of stars and the bending of light are not basic forces, but large-scale effects of quantum information encoded elsewhere. The proposal sounds fantastical, almost science fiction, yet it is grounded in serious mathematics and arises from the stubborn puzzles of black hole physics. The seeds were planted in the 1970s when Jacob Bekenstein and Stephen Hawking studied black holes. They discovered that black holes are not simply dead ends in space-time, swallowing matter and hiding it forever. Instead, black holes obey thermodynamic laws. They have entropy, a measure of information, content, and temperature associated with Hawking radiation. The shocking insight was that the entropy of a black hole is proportional not to its volume, but to the area of its surface, the event horizon. This meant that the information hidden in a black hole is somehow encoded on its boundary. That revelation shook the foundations of physics. In ordinary systems, entropy grows with volume. A gas in a box has entropy proportional to the number of particles inside. But black holes defied this expectation. Their entropy depended only on surface area. It was as if the three-dimensional interior did not exist, or at least did not matter, and only the two-dimensional boundary carried the essential information. Bekenstein and Hawking had stumbled onto a clue that space-time itself might be holographic. Years later, Gerard Hooft and Leonard Susskind expanded this idea into the holographic principle. They proposed that the maximum amount of information in any region of space is determined by the area of its boundary, not its volume. In other words, the universe may be like a hologram, with the true information written on a distant surface. Our three-dimensional reality would then be an emergent projection. Gravity, as part of that projection, would not be fundamental but derived. At first, the holographic principle was an elegant speculation. Then came the breakthrough known as ADS-CFT correspondence. Juan Maldacena, in 1997, proposed that a certain kind of universe with gravity, known as anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity living on its boundary. This duality provided a concrete example of holography in action. A higher dimensional spacetime with gravity could be fully described by a lower dimensional quantum system without gravity. What looked like two very different theories were in fact two languages describing the same reality. The implications are staggering. If spacetime and gravity can be translated into pure quantum information on a boundary, then perhaps gravity itself is nothing more than the collective behavior of entangled quantum states. The bending of spacetime, the fall of planets, the pull of stars, all could be illusions produced by quantum bits encoded on a surface beyond our reach. What we feel as weight might be the shadow of entanglement patterns shimmering in the quantum fabric of the cosmos. Of course, our universe is not anti-de Sitter space. It is not curled inward, but expanding outward, driven by dark energy. Yet the holographic principle may still apply in a broader sense. The mathematics of black holes and entropy continues to hint that information is never lost, only scrambled, and that the true bookkeeping of the cosmos happens not in volumes, but on surfaces. If this is correct, then everything we see is encoded elsewhere, and gravity is the illusion that results. This idea has not been proven, and many physicists remain skeptical. But the holographic principle has become one of the most influential concepts in theoretical physics, shaping the search for a quantum theory of gravity. It bridges the gap between relativity and quantum mechanics in a surprising way, not by forcing them together, but by revealing that they may be two faces of the same deeper truth. And so, from a hologram in the palm of your hand to the entropy of black holes, the idea emerges that reality itself may be a projection. Gravity, the most familiar of forces, may be nothing more than the large-scale illusion of quantum information encoded on a distant screen. The next part of our journey will dive deeper into this picture, exploring how holography connects with the thermodynamics of black holes and why many physicists now wonder whether space-time itself is stitched together by quantum information. The discovery that black holes carry entropy proportional to their surface area was more than a mathematical curiosity. It was a revolution that changed how physicists thought about information, energy, and even the meaning of space itself. If the entropy of a black hole is given by the area of its event horizon, then the maximum information a region of space can hold is not determined by how much volume it encloses, but by the size of its boundary. This is like saying that a library's knowledge is measured not by the number of books it can contain inside, but by the size of its outer walls. The larger the surface, the more information it can store. This conclusion is deeply counterintuitive. We are used to thinking that more space means more room for information. If you double the volume of a box, you expect to double the possible states of the system inside. But black holes suggest the opposite. A box filled with matter cannot hold more information than the area of its surface allows. Add too much matter, and the box collapses into a black hole, erasing the distinction between its contents and encoding everything on its boundary. Reality itself seems to enforce a cosmic bookkeeping rule. The universe is holographic. The holographic principle has remarkable consequences for gravity. If all the information in a region is stored on its boundary, then the gravitational field inside that region might be nothing more than the emergent effect of those boundary states. In this sense, gravity could be a mirage, the byproduct of quantum information projected inward. Just as the three-dimensional image on a hologram emerges from a two-dimensional plate, space-time geometry and its curvature may emerge from the entanglement of quantum bits. This is not just speculation, but is supported by concrete mathematics. The ADS-CFT correspondence shows that the dynamics of gravity in a higher dimensional space can be exactly equivalent to a quantum field theory, without gravity on the lower dimensional boundary. Imagine a four-dimensional space-time with gravity, completely describable by a three-dimensional quantum system. In such a picture, gravity is not fundamental, but a translation of quantum interactions into geometric language. The thermodynamics of black holes reinforces this vision. A black hole's temperature, entropy, and radiation all behave as though space-time itself is a thermodynamic system. Just as the laws of thermodynamics emerge from the statistical behavior of molecules, the laws of gravity may emerge from the statistical behavior of quantum information. Gravity becomes less like a force and more like a temperature, a large-scale effect with no single particle to carry it. Skeptics point out that ADS-CFT works in very specific cases, not in our real universe. Our cosmos is not anti-de Sitter space, but a nearly flat expanding universe. Translating holography into our reality is far from straightforward. Yet the principle continues to inspire because it offers something that neither relativity nor quantum mechanics can provide on their own, a way to reconcile them. In holography, gravity and quantum theory are not enemies but partners, two different languages describing the same information. If this view is correct, then every star, every planet, every human being is part of a projection from quantum data encoded on a vast cosmic boundary. Our most direct experiences of gravity, the pull of the Earth, the orbit of the Moon, the collapse of stars, are illusions in the same way that the three-dimensional image on a hologram is an illusion. They are real in our perception, but they arise from a deeper truth. And yet, if gravity is an illusion, it is an extraordinarily convincing one. Unlike the image in a hologram, which shimmers and fades if the light is wrong, gravity never fails. It holds galaxies together, shapes the paths of comets, and dictates the destiny of stars. If it is an illusion, then illusions can be powerful enough to guide the universe itself. The next step in this journey will look at how these holographic ideas connect to the broader picture of emergent gravity, where the pull we feel as weight might be nothing more than the statistical behavior of quantum information. From black hole horizons to cosmic structures, the suggestion grows that gravity is not what it seems, that the most familiar force may be nothing but the shadow of deeper physics. The more physicists studied black holes, the clearer it became that they were not just exotic objects lurking in space, but windows into the fundamental nature of reality. The famous paradox raised by Stephen Hawking made this unavoidable. If black holes evaporate through Hawking radiation, then information seems to be lost forever, destroyed in violation of quantum mechanics. But quantum theory insists that information cannot be destroyed. Something had to give. Either quantum mechanics was incomplete, or our understanding of gravity was. The holographic principle offered a daring resolution. Information is not lost. It is encoded on the horizon, hidden in the shimmering surface of the black hole, waiting to be scrambled and released. This idea extends beyond black holes to space-time itself. If horizons encode information on surfaces, why not the entire universe? Perhaps everything we see is written on a cosmic horizon at the edge of space-time, projected inward into the three-dimensional world we experience. This would mean that our reality is fundamentally information theoretic, a grand computation unfolding on a distant boundary. Space-time curvature, which we call gravity, would then be a large-scale effect of the way this information is organized. To make this more concrete, consider how entanglement ties quantum systems together. Entangled particles share states, no matter how far apart they are. Their properties are linked in ways that defy classical logic. Now imagine vast networks of entanglement weaving through the universe. The holographic principle suggests that these patterns of entanglement could create the fabric of space-time itself. Where entanglement is dense, space stretches smoothly. Where it is sparse, space may thin or even tear. Gravity, in this picture, is simply the geometry that emerges from entanglement. This view changes the meaning of Einstein's curved spacetime. Instead of matter-bending spacetime, it may be that quantum information organizes itself in such a way that geometry appears, and the bending we observe is the shadow of those deeper connections. It is a profound shift, as though we have been mistaking the projection for the thing itself, the apple that falls, the planet that orbits, the light that bends around a star. All of these are real experiences, but their root may lie in invisible webs of quantum entanglement encoded on a faraway surface. For many, this possibility is exhilarating. It suggests that the rift between relativity and quantum mechanics may not be a clash after all, but a misunderstanding. Relativity describes the emergent geometry of space-time. Quantum mechanics describes the underlying information. The holographic principle unites them by showing how one can emerge from the other. Gravity, then, is not missing from the quantum world. It is born from it. Of course, skepticism remains. The mathematics of holography works beautifully in certain idealized universes, but has yet to prove itself in our expanding cosmos. Some physicists warn against taking the analogy too literally. Others argue that even if holography is not exact, it points the way toward a new paradigm where information, not space-time, is the foundation. Whether exact or approximate, the holographic principle has already reshaped physics. It has become a guiding thread in the search for a theory of quantum gravity, influencing string theory, black hole research, and even cosmology. It challenges us to see gravity not as a force but as an emergent illusion, a projection of quantum data encoded on boundaries beyond our reach. And so the holographic universe leaves us with a staggering thought. The solidity of the ground beneath our feet, the vastness of galaxies in the night sky, the inexorable pull of the Earth. All of it may be a three-dimensional image projected from information on a distant surface. The most familiar of forces may be the most deceptive, a cosmic mirage woven from quantum bits. The next step in our journey carries us to one of the most daring attempts to formalize this idea, the proposal of Eric Verlinde, who argues that gravity is not fundamental at all, but an entropic force, an emergent phenomenon born from information and statistics. If true, then gravity may be not just holographic, but thermodynamic, as illusory, and yet as real as the warmth of fire or the pressure of air. For centuries, gravity has been treated as one of nature's fundamental forces, but in recent years, a bold alternative has emerged. Eric Verlinde, a Dutch theoretical physicist, has argued that gravity is not a force at all, but an emergent phenomenon, something that arises from the collective behavior of underlying quantum information. In this view, what we call gravity is as emergent as temperature, which arises from the average motion of countless molecules, or as pressure, which comes from the collisions of atoms in a gas. Verlinde's proposal invites us to reconsider everything we thought we knew about the most familiar of forces. The idea began with a simple observation about information and entropy. Entropy is the measure of disorder in a system, or more precisely, the number of possible microscopic configurations that can give rise to the same macroscopic state. Heat is not a substance but a reflection of entropy. When molecules jostle and collide, their microscopic chaos creates the sensation we call warmth. Verlinde wondered, could gravity be another such emergent effect, not a fundamental interaction, but a byproduct of information at a deeper level? He proposed that gravity emerges from changes in entropy associated with the position of matter. Imagine a particle approaching a holographic screen, a notional surface that stores information about the system inside. As the particle moves closer, the entropy of the screen changes. This change in entropy creates a statistical tendency for the particle to move, and that tendency manifests as what we call a gravitational pull. Gravity, in this sense, is not a fundamental force, but an entropic force, arising from the universe's constant drive to maximize entropy. This was more than philosophy. Verlinde showed that his approach could reproduce Newton's law of gravitation, the familiar inverse square law, which describes how gravitational attraction weakens with distance, appeared naturally from entropic considerations. It was a startling result. Newton's timeless law could be derived not from fundamental forces, but from the mathematics of entropy and information. But Verlinde did not stop there. He extended his theory to cosmic scales, where gravity shows puzzling behavior. Galaxies spin faster than they should, if only visible matter were present. According to Newton and Einstein, they should fly apart unless there is additional unseen mass. For decades, physicists have attributed this discrepancy to dark matter, a mysterious substance that outweighs normal matter by a factor of 5, but has never been directly detected. Verlinde suggested a different explanation. He argued that the observed galactic motions might be the natural outcome of emergent gravity, without any need for dark matter. The claim was bold, and it drew both interest and skepticism. If true, Verlinde's proposal could resolve one of the greatest mysteries of cosmology without inventing a new form of matter. It would mean that the universe is stranger, but perhaps simpler, with gravity as an illusion born from the statistical mechanics of quantum information. Yet critics pointed out that while Verlinde's equations fit certain galactic rotation curves, they struggled to account for all observations, especially the detailed patterns of gravitational lensing and the large-scale structure of the universe. Still, the audacity of Verlinde's idea has forced physicists to consider new ways of thinking. It reminds us that what seems most real may turn out to be emergent. Heat, pressure, and elasticity all once seemed fundamental, until science revealed them as macroscopic consequences of microscopic laws. Gravity may belong to the same category. If Verlinde is right, then space-time itself is not a stage but a construction, and gravity is the illusion that guides the performance. In this vision, the universe becomes a grand interplay of information, entropy, and emergence. The weight we feel pressing our feet to the ground, the orbits of planets, the collapse of stars, all would be nothing more than statistical byproducts of deeper rules. It is a breathtaking thought that the most familiar of forces may be the most illusory, a cosmic thermodynamic mirage that shapes the destiny of galaxies. The next part of this chapter will follow the consequences of Verlinde's idea exploring how emergent gravity challenges the dark matter paradigm and why many remain cautious, insisting that extraordinary claims require extraordinary evidence. Verlinde's challenge to dark matter struck at the heart of modern cosmology. For decades, astronomers have been confronted with evidence that something unseen holds galaxies together. When they measure how stars orbit within galaxies, the outer stars move too quickly. According to Newton and Einstein, those galaxies should be torn apart. To explain their stability, scientists proposed that most of the universe's mass is invisible, a mysterious dark matter that does not emit or absorb light, but reveals itself only through gravity. The dark matter hypothesis became the dominant explanation. It accounts not only for galactic rotation curves, but also for the behavior of galaxy clusters, for the bending of light through gravitational lensing, and for the distribution of cosmic structures across billions of light years. Yet despite decades of searching, no dark matter particle has ever been detected. Vast underground detectors, orbiting observatories, and particle colliders have all come up empty. This absence has left a crack open for alternatives, and into that crack, Verlinde placed his bold proposal. In his emergent gravity framework, the need for dark matter disappears. The excess gravitational pull in galaxies, he argued, arises naturally from the entropic response of space-time. As matter moves, it alters the entropy stored in the holographic information of the universe. This entropic adjustment creates an additional effective force, one that mimics the effect of dark matter. Instead of invisible particles, the cosmos may simply be governed by deeper information rules that make galaxies appear heavier than they are. When Verlinde published his equations, the response was electric. Some saw in his work a radical but elegant way to bypass the dark matter mystery. Others cautioned that while his theory explained certain galactic data, it did not yet match the precision of dark matter models across the full range of observations. In particular, the detailed gravitational lensing seen in galaxy clusters seemed more naturally explained by actual unseen mass. The cosmic microwave background also fit neatly with the presence of dark matter, making Verlinde's alternative difficult to reconcile with the big picture. Yet the debate is far from settled. Emergent gravity forces scientists to ask whether the absence of dark matter detection is a failure of technology or a sign that dark matter does not exist at all. If Verlinde is correct, then the billions of dollars spent hunting for exotic particles may be chasing a ghost, while the true answer lies in rethinking gravity itself. That possibility is both thrilling and unsettling. It would mean that the universe is built not from hidden matter, but from hidden information, and that gravity is the visible tip of an entropic iceberg. Critics argue that Verlinde's theory is still in its infancy. Its equations are elegant but incomplete, and they struggle to predict cosmic phenomena as precisely as the dark matter model. Moreover, the dark matter hypothesis, despite its mystery, has extraordinary predictive power. It fits not only galactic scales but cosmological ones, allowing scientists to simulate the formation of the universe with remarkable accuracy. Emergent gravity must do more than explain rotation curves. It must rival this predictive success across all observations. And yet, even with these challenges, Verlinde's proposal has left a mark. It has forced physicists to think of gravity in new terms, not as a fundamental law etched into the fabric of space-time, but as an emergent phenomenon tied to entropy and information. Whether or not emergent gravity replaces dark matter, it sharpens the question, what if the universe we see is not made of hidden particles, but of hidden rules? The debate continues, unresolved. On one side stands the weight of evidence for dark matter. On the other stands the radical possibility that gravity itself is emergent. To decide between them will take more than mathematics. It will require experiments and observations that push the boundaries of what we can see. The final part of this chapter will look at how Verlinde's vision fits into the larger search for meaning, why many remain skeptical, and how the idea of emergent gravity changes our understanding of what it means for a force to be real. The skepticism surrounding Verlinde's proposal is not born of hostility, but of caution. Physics has seen bold claims before, and history is littered with ideas that promise to overturn orthodoxy, but fail to match the weight of observation. Extraordinary claims demand extraordinary evidence, and emergent gravity is nothing if not extraordinary. To suggest that gravity, the very force that sculpts the universe, is not fundamental, but a thermodynamic effect of information, is to challenge the foundation of centuries of science. Many physicists argue that dark matter, despite its invisibility, remains the more conservative explanation. It preserves the framework of general relativity while accounting for the data across cosmic scales. It provides a consistent picture that fits the cosmic microwave background, galaxy clusters, and large-scale structure. Emergent gravity, elegant though it may be, has yet to achieve this breadth. Without clear predictions that match observations better than dark matter, it remains an intriguing alternative rather than a replacement. And yet, there is something compelling about Valinde's vision. It resonates with the broader movement in theoretical physics that sees space-time not as a given, but as emergent. From black hole entropy to holography, from quantum entanglement to information theory, a pattern is emerging. What we perceive as geometry may be the shadow of something deeper. In this light, Valinde's proposal is not an isolated idea, but part of a larger shift. It suggests that our sense of weight, our experience of falling, our picture of galaxies, all may be illusions born from the hidden architecture of information. If gravity is emergent, what does that mean for our understanding of reality? It means that the most direct force we feel, the pull that shapes every step we take, is not written into the universe at its foundation. It is a large-scale consequence of something invisible, something woven into the very logic of quantum information. Just as temperature has no meaning for a single atom, but emerges from the dance of many, gravity may have no meaning at the quantum level. It appears only when vast numbers of quantum bits weave together into space-time itself. This perspective humbles us. It reminds us that what feels solid may be a mirage, that our deepest intuitions about force and motion may be provisional, waiting to be replaced by deeper truths. It challenges us to see beyond appearances, to recognize that the universe may not be built on particles and fields alone, but on information and entanglement. Gravity, in this picture, is not an enemy of quantum mechanics, but its offspring, a byproduct of the quantum world writ large. The implications reach beyond physics into philosophy. If gravity is emergent, then reality itself may be layered, with our three-dimensional experience only a projection of hidden rules. What we call fundamental may be nothing more than the latest illusion stripped away by science. This is not to diminish gravity's power, but to place it in a new context. An illusion can shape galaxies. An illusion can govern the fate of stars. Illusions in physics do not vanish when exposed. They reveal deeper realities beneath them. As our journey continues, we turn to the next piece of this puzzle, the role of quantum entanglement. For if gravity emerges from information, then perhaps space-time itself is built from the invisible threads of entanglement. The next chapter explores this radical idea, where wormholes and quantum links become one, and where the geometry of the universe may be nothing more than the fabric of quantum connections. In the world of quantum mechanics, nothing is more mysterious than entanglement. Two particles can be prepared in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. It is as though an invisible thread links them across space, binding their fates together. Einstein famously called this spooky action at a distance, for it seemed to defy his principle that nothing can travel faster than light. Yet experiment after experiment has confirmed that entanglement is real, one of the strangest and most reliable features of quantum theory. At first, entanglement seemed like a curiosity, a strange corner of the quantum world, but over time, physicists began to suspect that it might be more than that. Perhaps entanglement is not just a feature of particles, but the foundation of reality itself. Perhaps space and even gravity emerge from networks of entanglement, woven together into the fabric we call space-time. If so, then gravity is not a fundamental force, but the geometry of entanglement, expressed on a cosmic scale. The seeds of this idea were planted in the 1990s, when theorists studying black holes and holography realized that information seemed to be stored in patterns of entanglement. Later, in 2013, Juan Maldacena and Leonard Susskind put forward a bold conjecture: ER equals EPR. The letters stand for two famous concepts. ER refers to Einstein and Nathan Rosen's wormholes, bridges through spacetime that connect distant regions. EPR refers to the Einstein-Podolsky-Rosen paper, which introduced the paradox of entanglement. Maldacena and Susskind suggested that these two ideas are the same, that entangled particles are connected by tiny wormholes. If true, this means entanglement is the glue of spacetime. Every link of entanglement is a thread, and together, these threads weave the geometry of the universe. Wormholes, once thought of as exotic tunnels through space, may simply be the geometric expression of entanglement. What we call space may be nothing more than a vast tapestry of quantum links, and gravity, the bending of that space, may be the large-scale effect of how these links are organized. This picture is radical, but it explains puzzles that once seemed intractable. For example, the black hole information paradox, where Hawking radiation seemed to destroy information, can be reinterpreted in terms of entanglement across the horizon. Information is not lost but encoded in quantum links. The holographic principle, which suggests spacetime is a projection of information on boundaries, gains a natural explanation. Those boundaries describe patterns of entanglement that give rise to space. Entanglement also explains why spacetime feels continuous. Imagine tearing apart a fabric woven of threads. If the threads remain intact, the cloth holds together. If they are cut, holes form. In the same way, dense entanglement creates smooth geometry, while loss of entanglement may create ruptures in spacetime. Gravity, in this vision, is nothing more than the curvature of the entanglement web. Of course, this idea is speculative. We do not yet know how to derive Einstein's equations directly from entanglement, though progress has been made. In some holographic models, the geometry of space does indeed emerge from entanglement entropy, a measure of how much quantum information is shared across boundaries. These models show that when entanglement patterns change, so does the geometry, hinting that space itself may be built from quantum connections. If this is correct, then our everyday experience of gravity is an illusion of entanglement. The apple falls not because of a force pulling it downward, but because the geometry of entanglement curves the space around it. Planets orbit stars not because of invisible gravitons, but because entanglement weaves spacetime into paths that guide their motion. The pull we feel is real, but it is the shadow of something deeper, the invisible quantum links binding the universe. This way of thinking transforms our place in the cosmos. It means that the distance between stars is not absolute, but depends on the entanglement fabric connecting them. It means that wormholes and entangled particles are two sides of the same coin, threads in a cosmic network that underlies all reality. And it means that gravity, the most familiar of forces, is not fundamental, but emergent, a mirage cast by quantum entanglement. The next part of this chapter will explore how physicists are trying to test this idea, from experiments that probe entanglement in the laboratory to cosmological observations that may reveal its fingerprints. If spacetime is truly woven from entanglement, then every measurement of gravity is also a measurement of quantum connections. Entanglement has always seemed like a fragile phenomenon, something that belongs only to the world of particles and laboratory experiments. Yet, if spacetime itself is woven from entanglement, then this strange property is not fragile at all. It is the most robust feature of the universe, the deep order that allows reality to exist. To glimpse how this might work, physicists have begun to think of space as a kind of network. In such a network, each point of space is not defined by coordinates alone, but by how it is entangled with others. Distance is not an absolute separation, but a measure of the strength of entanglement between regions. This shift in perspective explains why spacetime is smooth and continuous at large scales, but quantum and uncertain at small ones. At macroscopic levels, countless entanglement links overlap to create geometry that looks classical, just as countless molecules create the smoothness of air. But at microscopic scales, the discreteness of entanglement becomes visible, and space itself may appear granular or foamy. The seamless geometry we take for granted is only the statistical average of countless quantum threads. Experiments are beginning to probe this connection, though the challenge is enormous. Recently, physicists have explored the possibility that entanglement between tiny masses might create measurable gravitational effects. The idea is to place two small objects in superposition, each capable of being in two places at once, and then entangle them. If their mutual gravitational attraction shows signatures of quantum entanglement, it could be the first evidence that gravity itself is quantum, not classical. Such experiments are in their infancy, but they represent the first steps toward testing whether spacetime really is built from entanglement. Another path comes from the study of black holes. The holographic principle suggests that the information content of a black hole is determined by entanglement across its horizon. Recent advances in theoretical physics have shown that entanglement entropy can reproduce the geometry of spacetime near black holes. In other words, by studying how quantum states are entangled, one can reconstruct the shape of space itself. This is not just metaphor, but mathematics. The entanglement structure determines the geometry. Even in cosmology, entanglement is leaving its mark. The early universe was a seething quantum system, filled with fluctuations that became seeds of galaxies. These fluctuations were not independent but entangled across vast distances. Today, when astronomers measure the cosmic microwave background, they see patterns that may carry the imprint of those entangled states. The entire large-scale structure of the universe, from clusters of galaxies to cosmic voids, may be the fossil record of quantum entanglement, stretching across billions of light-years. If these ideas are correct, then the familiar picture of space-time as a stage where events unfold is incomplete. There is no stage. The play itself, the actors and their dialogues, create the stage through entanglement. Remove the entanglement, and the stage vanishes. Gravity, in this view, is the consequence of how that stage curves under the weight of entanglement patterns. It is the geometry of information, not the pull of a fundamental force. Of course, we must remain skeptical. The mathematics of entanglement and space-time is still developing, and experiments are far from conclusive. But the beauty of the idea is undeniable. It unites the strangest feature of quantum mechanics with the most familiar feature of our everyday lives. It suggests that the spooky action Einstein disliked so much may not be an oddity at all, but the very glue that holds the cosmos together. The next part of this chapter will bring these threads together, exploring the philosophical stakes of a universe where gravity is not a force, but a consequence of quantum entanglement, and where space-time itself is no more fundamental than the warmth of a flame or the pressure of the air. If space-time truly emerges from entanglement, then our understanding of reality must be rewritten from the ground up. We would no longer think of the universe as a container filled with matter and energy, but as a vast web of quantum information, whose entanglement gives rise to the very notion of distance and geometry. Gravity would not be a force in the traditional sense, nor even a field waiting to be quantized. It would be a mirage created by the collective behavior of countless quantum links, an effect as real as the warmth of fire, but as emergent as temperature itself. This possibility changes the way we think about what is fundamental. The apple that falls from the tree, the orbit of the moon, the bending of light around the sun, all these phenomena are real in the same way that waves are real on the surface of the ocean. But just as waves are not fundamental objects, gravity may not be fundamental either. It may be the large-scale behavior of something deeper, invisible to us, but encoded in the entanglement of quantum states. There is a philosophical challenge in this view. If space and time are emergent, what lies beneath them? We are accustomed to thinking in terms of geometry, of points and distances, but if these concepts are not primary, then reality at its root may not resemble anything we can picture. It may be pure information, mathematical relations without space, without time, without position. In such a world, entanglement is not a connection across space. It is the structure from which space itself emerges. Some physicists embrace this radical possibility, seeing in it a way to unify the two great pillars of science. Relativity describes the geometry of space-time. Quantum mechanics describes the behavior of information. If space-time is born from entanglement, then relativity and quantum theory are no longer rivals, but parts of a single story. The tension between the cosmic and the microscopic dissolves. They are not two incompatible languages, but two levels of description. Others remain cautious, pointing out that while the mathematics of entanglement and holography is promising, it has not yet been tested in the real universe. Our cosmos is not the anti-de Sitter space where many of these ideas were developed. Our universe is expanding, driven by dark energy, and the translation from theory to reality is not simple. Until experiments confirm that entanglement shapes space-time in our world, the idea remains a bold conjecture. But science thrives on bold conjectures, and history shows that today's speculation can become tomorrow's foundation. Whether or not entanglement truly builds space-time, the idea has already reshaped how physicists think. It has inspired new ways to approach the puzzles of black holes, quantum gravity, and the information paradox. It has encouraged experiments that would once have seemed impossible, such as testing whether entanglement itself can create measurable gravitational effects in the laboratory. And so, the image of reality shifts once again, from Newton's invisible force to Einstein's curved space-time, and now to the vision of entanglement as the weaver of geometry. Gravity continues to evolve. Each step reveals not only more about the cosmos, but more about the limits of human understanding. Perhaps gravity is not a fundamental force at all, but the shadow of quantum entanglement, a grand illusion cast across the vast theater of the universe. Our journey now moves to the frontier where theory meets experiment. If gravity is emergent, if it is a product of information, then we must find ways to test it. In the laboratory, in the motions of galaxies, in the bending of light across billions of light years, the universe offers clues. The next chapter turns to these tests, asking how we might probe the illusion of gravity and discover whether the most familiar of forces is truly real or only the shimmering reflection of a deeper truth. Theories can be bold and beautiful, but in the end, science lives and dies by experiment. If gravity is an illusion, if it emerges from entropy or from networks of entanglement, then there must be ways to test this idea. The task is formidable. Gravity is the weakest of the known interactions, and quantum effects are subtle, even for the strongest forces. Yet physicists are not deterred. Across the globe, in laboratories and observatories, they are designing experiments and observations that may reveal whether gravity is truly fundamental or whether it is the grandest illusion in the cosmos. The first line of testing begins on the smallest scales. Gravity is so feeble between tiny objects that it is often ignored in particle physics. But new experiments are trying to measure gravitational interactions at microscopic distances. The idea is simple but revolutionary. Place two small masses in superposition, entangle them, and watch how they influence one another. If the gravitational field itself becomes entangled, then gravity must have a quantum character. If no entanglement appears, then perhaps gravity is not fundamental. Such tests are delicate beyond imagination. A single vibration from the environment can destroy the fragile quantum states, yet advances in technology are bringing them closer to reality. Another approach comes from the study of gravitational waves. These ripples in space-time, detected by the LIGO observatories, are the triumph of Einstein's theory. But some physicists hope that with more sensitive detectors, we might see signatures of quantum behavior within them. If gravitational waves arrive with a faint quantum granularity, it could point to gravitons. If they remain smooth, perhaps gravity is emergent. The signals are faint, the noise is great, but the possibility is tantalizing. Cosmology offers another arena for tests. The motions of galaxies, the bending of light by clusters, the expansion of the universe itself, all are governed by gravity. For decades, astronomers have invoked dark matter to explain why galaxies spin faster than expected and why clusters lens light more strongly than visible matter allows. But if emergent gravity is real, perhaps these phenomena can be explained without unseen particles. Verlinde's proposal makes specific predictions about how galaxies should rotate. Some data seem to fit, others do not. The debate remains alive, and new surveys of the cosmos may provide the decisive evidence. The cosmic microwave background, the faint glow of the early universe, also offers clues. Tiny fluctuations in its temperature and polarization are the fossil record of the first moments after the Big Bang. If gravity was emergent from quantum entanglement, those early patterns may carry its fingerprints. Experiments searching for subtle swirls in the polarization of the cosmic background hope to detect primordial gravitational waves, perhaps revealing whether space-time itself has a quantum grain. Even the study of black holes may test emergent gravity. If information is preserved through entanglement on the horizon, then the evaporation of black holes should follow patterns that differ from a classical description. New ideas like the firewall paradox and the page curve attempt to describe how information escapes. Though direct observation of black hole evaporation is beyond our reach, careful theoretical work combined with astronomical data may hint at whether gravity is fundamental or emergent. Each of these tests is uncertain, each fraught with challenges, but together they form a web of possibility. Step by step, experiment by experiment, physicists are probing the illusion of gravity. They are asking whether the most constant force of our lives is truly written into the foundations of nature, or whether it is the shimmering projection of something deeper. The next part of this chapter will explore these tests more closely, showing how laboratories on Earth and telescopes in space are working together to unravel the mystery of gravity's true nature. The dream of testing whether gravity is emergent or fundamental has drawn physicists into some of the most delicate experiments ever imagined. On Earth, the focus is on the quantum realm, where gravity's weakness makes it nearly impossible to measure. Still, progress is being made. One proposal involves suspending tiny masses smaller than grains of sand and cooling them to near absolute zero so that they can be placed in quantum superpositions. If two such masses are entangled by their mutual gravitational attraction, then gravity itself must be quantum in nature. Such an outcome would support the idea of gravitons, placing gravity firmly in the family of fundamental forces. If, however, no entanglement appears, it may point, instead, to an emergent origin. These experiments are fiendishly hard. Any vibration from the environment, any stray photon of heat, can collapse the superposition and ruin the measurement. Laboratories must isolate the masses from seismic noise, shield them from cosmic rays, and maintain temperatures colder than the depths of interstellar space. The technology to do this is only now becoming available. It may take decades before results are clear, but even the attempt represents a revolution. For the first time, humanity is trying to test the quantum nature of gravity directly, not through astronomical observation, but in carefully controlled laboratory settings. Meanwhile, the cosmos provides its own natural laboratories. Astronomers have long studied the behavior of galaxies, which rotate too quickly for the amount of visible matter they contain. The orthodox explanation invokes dark matter, unseen particles that outweigh normal matter 5 to 1. But Verlinde's emergent gravity proposes a different cause, an entropic effect that mimics dark matter. To test this, astronomers compare the predicted rotation curves from Verlinde's theory to actual measurements. Some galaxies seem to match, others deviate. The jury is still out. Gravitational lensing offers another test. When light passes near a massive cluster of galaxies, it bends, creating arcs and distortions that reveal the total mass present. Dark matter models predict specific patterns of lensing that have been confirmed in detail. Emergent gravity, in its current form, struggles to reproduce all these observations. This is one reason many astrophysicists remain skeptical. For emergent gravity to replace dark matter, it must explain not just some phenomena, but all of them, from the smallest galaxies to the largest structures in the universe. Then there are gravitational waves. Detected for the first time in 2015, they have opened a new window into the universe. Generated by colliding black holes and neutron stars, these ripples in space-time confirm Einstein's predictions to astonishing precision. But as detectors improve, physicists hope to search for deviations that might hint at quantum or emergent behavior. If the waves show evidence of discrete quanta, the gravitational equivalent of photons, it would support the graviton picture. If they remain smooth, emergent theories might gain traction. The signals are faint, but the stakes are immense. Cosmic background radiation adds yet another layer of testing. The polarization patterns in this ancient light could reveal primordial gravitational waves from the earliest moments of the universe. If found, they might carry signatures that distinguish between fundamental and emergent gravity. Several experiments are underway, scanning the heavens for this faint imprint. Each of these efforts illustrates the same truth. Testing gravity at the quantum or emergent level is not easy. Unlike electromagnetism, where photons can be produced and measured in abundance, or the nuclear forces, where particles can be probed in accelerators, gravity hides behind its weakness. It demands patience, precision, and creativity, yet the payoff would be immense. To confirm or deny gravity's emergent nature would not only answer a profound scientific question but reshape our understanding of reality itself. The final part of this chapter will ask what it means if the tests succeed, and what it means if they fail. Can gravity truly be reduced to information, or will it remain the one force that resists the quantum net? If the experiments succeed in showing that gravity can entangle, that tiny masses influence one another in ways that reveal a quantum signature, then the graviton picture will be strengthened. Gravity will join the other forces in the quantum framework, no longer the odd one out, but a full member of the family. Such a discovery would not only be a triumph for quantum field theory, but also a stepping stone toward a unified theory of all forces. Physicists could finally begin to stitch together a quantum theory of space-time, confident that gravity belongs in the same tapestry as electromagnetism and the nuclear interactions. The path would still be long, but the direction would be clear. But what if the opposite happens? What if the experiments show no entanglement, no quantum character in gravity? Then the dream of gravitons may fade, and emergent theories will gain momentum. If gravity cannot be quantized, it may not be a force at all, but an illusion born from entropy or entanglement. In that case, the most familiar of forces would be revealed as a large-scale phenomenon, like temperature or pressure, powerful and real, but not fundamental. Verlinde's vision of entropic gravity, or the holographic idea that space-time emerges from quantum information, would no longer be curiosities, but necessities. physics would shift from seeking gravitons to seeking the hidden rules of information that give rise to geometry. The consequences extend to cosmology. If emergent gravity is confirmed, the dark matter paradigm may need to be revised. Galaxies, clusters, and the structure of the universe would need to be reinterpreted, not in terms of invisible particles, but in terms of the hidden architecture of information. Dark energy, too, might be understood in new ways. Instead of a mysterious fluid driving cosmic acceleration, it could be the entropic effect of quantum states on the cosmic horizon. The universe itself would be reimagined not as a stage of matter and forces, but as a grand computation of quantum information. There is also the possibility that the tests remain inconclusive. Gravity may be too weak, the effects too subtle for us ever to measure directly. In that case, the debate may remain unresolved for generations, leaving physicists to argue from theory rather than observation. Even this outcome has meaning. It would remind us of the limits of science, of how some truths may remain hidden, no matter how hard we try to uncover them. But history shows that patience pays. Atoms were once invisible, neutrinos undetectable, gravitational waves a dream. Perhaps gravitons or emergent signatures will one day join the list of triumphs wrested from impossibility. For now, the question remains open. Is gravity a quantum force carried by gravitons, or is it the large-scale mirage of entropy and entanglement? The experiments underway will not answer this overnight, but they are the first steps. They represent humanity's determination to test even the most elusive of ideas, to ask whether the ground beneath our feet is fundamental or an illusion woven from deeper threads. And so the story of gravity continues to unfold, from Newton's apple to Einstein's curved spacetime, from holograms to entropy, and now to laboratory entanglement and cosmic observations. Whether illusion or not, gravity still rules the cosmos. It guides the stars, sculpts galaxies, and shapes our every movement. Its mystery is not a weakness, but a sign that the universe has more to reveal. Our journey now turns back to the most enigmatic objects in the universe, black holes. If any place can reveal the truth about gravity, it is these cosmic abysses where space-time bends to its breaking point. The next chapter will explore the information paradox, the evaporation of black holes, and what they can teach us about whether gravity is truly fundamental or the most powerful illusion of all. Black holes are the strangest children of Einstein's equations. They are places where gravity overwhelms every other force, where space-time itself caves in, forming horizons from which nothing can escape. To fall into a black hole is to vanish from the universe's stage, leaving behind only a dark silhouette against the stars. For decades, black holes were thought to be silent, eternal prisons, swallowing matter and energy without a trace. But then came the paradox, a challenge so severe that it has shaken the very foundations of physics. What happens to information inside a black hole? The paradox begins with the simplest of principles. In quantum mechanics, information is never lost. A system evolves from one state to another, but the record of its past is always encoded in the present, even if scrambled beyond recognition. In relativity, however, black holes seem to erase information completely. Anything that crosses the horizon is hidden forever. If the black hole eventually evaporates through Hawking radiation, as Stephen Hawking discovered in the 1970s, then the information about what fell in appears to vanish from the universe. This would break the most sacred rule of quantum theory. Hawking radiation itself is already a shock. According to Einstein's equations, black holes should be absolute traps. Yet quantum effects, near the horizon, create pairs of particles from the vacuum. One falls in, the other escapes, carrying energy away. Over immense timescales, the black hole shrinks and ultimately evaporates into nothing. But the radiation is thermal, like the heat from a fire, carrying no information about what was inside. If the black hole disappears completely, then the information about its contents seems to vanish too. This is the black hole information paradox. The paradox has divided physicists for decades. If information is lost, then quantum mechanics is incomplete, and our most successful theory of the microscopic world must be rewritten. If information is preserved, then something in our understanding of gravity must change, because classical black holes cannot return what they swallow. Between these two extremes lies a mystery that has driven some of the boldest ideas in modern physics. Some argue that information is preserved in subtle correlations within Hawking radiation, invisible in Hawking's original calculation, but present in a more complete theory. Others suggest that information is encoded on the event horizon itself, a holographic surface storing everything that falls in, to be released slowly in the outgoing radiation. Still, others propose radical new structures at the edge of black holes, firewalls, or fuzzballs, replacing the smooth geometry predicted by Einstein with exotic quantum states that can safeguard information. Whatever the solution, the information paradox forces us to confront the nature of gravity. If information is preserved, then gravity may be emergent from quantum information, a mirage shaped by entanglement and entropy. If information is lost, then quantum mechanics itself may need to be revised, breaking the most successful framework in the history of science. Either path reshapes our vision of the universe. Black holes, once thought of as silent monsters, have become laboratories for the deepest questions in physics. They are where relativity and quantum theory collide, where gravity reveals its most paradoxical face. The next part of this chapter will explore the competing solutions to the paradox and what they tell us about whether gravity is truly fundamental or only the most convincing illusion in nature. The paradox has inspired solutions that range from cautious refinements to radical overhauls of physics. One of the most compelling comes from the holographic principle. If all the information about what falls into a black hole is encoded on its surface, then nothing is truly lost. The event horizon becomes a kind of cosmic ledger, recording every detail in microscopic degrees of freedom. As the black hole evaporates, this information is gradually released in the subtle correlations of Hawking radiation. The radiation may look thermal at first glance, but hidden within it is the scrambled record of everything that entered. In this view, the paradox dissolves, not by rewriting quantum mechanics, but by recognizing that gravity is emergent from information. Another proposal is the firewall hypothesis. This idea suggests that the smooth horizon predicted by Einstein does not exist. Instead, a wall of high-energy quanta forms at the edge of the black hole, incinerating anything that tries to cross. The firewall would preserve information by preventing it from ever disappearing into the abyss. But this solution comes at a heavy cost, because it violates the equivalence principle, one of the cornerstones of general relativity. According to Einstein, an observer falling into a black hole should feel nothing unusual at the horizon. A firewall would shatter that picture. Many physicists resist this idea, but it remains on the table because the paradox demands resolution. String theory offers another vision, the fuzzball proposal. In this framework, black holes are not smooth objects with empty interiors, but tangled clumps of strings and brains. The fuzzball has no central singularity, no empty space behind a horizon, only a chaotic mess of quantum states. Information is never hidden but spread throughout the fuzzball, encoded in its structure. Radiation emitted from the fuzzball can carry information directly, avoiding the paradox. This idea preserves both quantum mechanics and unitarity, but it requires accepting a drastically different picture of what a black hole island. Perhaps the most elegant approach is the Page curve, named after Don Page. It predicts that Hawking radiation begins thermal, but gradually becomes more informative as the black hole shrinks. Early radiation carries little information, but later radiation is highly correlated, such that the full set encodes everything that fell in. Recent advances, using holography and quantum information theory, have shown that the Page curve can indeed emerge from certain models. This suggests that black holes do not destroy information after all. They simply scramble it so thoroughly that recovering it would be practically impossible. Each of these solutions tells a different story about gravity. Firewalls and fuzzballs suggest that Einstein's smooth spacetime is incomplete, that new physics waits at the horizon. The holographic principle suggests that spacetime itself is emergent from quantum information, with gravity as its large-scale illusion. The Page curve reinforces the idea that quantum mechanics remains intact, that information is never lost, and that gravity must yield to the deeper rules of entanglement. No single answer has yet triumphed. Observationally, black holes remain distant and shrouded in mystery. Yet theory continues to evolve, weaving together holography, entropy, and entanglement into a picture where gravity is not fundamental, but emergent. The paradox, far from being a flaw, has become a beacon, guiding physicists toward a new understanding of reality. The final part of this chapter will explore what these ideas mean for the very concept of reality. If black holes can scramble but not destroy information, then gravity may be less a force than an accountant, keeping the cosmic books balanced. But if information can truly vanish, then perhaps we have reached the limit of quantum mechanics itself. If black holes truly preserve information, then the universe is consistent at its deepest level. Quantum mechanics remains intact, gravity is emergent from hidden threads of information, and the paradox is a window into a new paradigm. In this picture, a black hole is not a cosmic eraser, but a cosmic scrambler. What falls in is not lost, but transformed, mixed beyond recognition, then released, bit by bit, through Hawking radiation. The information is still there, though scattered so completely that no observer could ever piece it back together. The laws of physics remain whole, even if they mock our human ability to recover order from chaos. But if information is lost, then the implications are staggering. Quantum mechanics, long celebrated for its perfect unitarity, would need to be revised. A new framework would be required, one that accepts that the universe can forget. Such a framework would change everything, from our understanding of microscopic particles to our conception of time itself. The loss of information would mean that the arrow of time is not simply statistical but fundamental, that the past can vanish irretrievably into the void. Many physicists resist this possibility, not only because it breaks quantum mechanics, but because it undermines the very predictability of science. The truth may lie somewhere unexpected. Perhaps black holes preserve information, but only in ways that reveal the emergent nature of space-time. Perhaps the paradox is not a flaw to be patched, but a clue that gravity is not fundamental at all. If space-time itself is woven from entanglement, then horizons and radiation are simply features of that weave. The paradox dissolves once we recognize that geometry is not primary. That information is the bedrock and gravity, the illusion. For the moment, the debate is unresolved. Firewalls, fuzzballs, holography, page curves, each offers insight, none delivers certainty. Black holes remain distant laboratories, their secrets encoded in faint X-ray emissions and gravitational waves. But even without decisive proof, the paradox has already transformed physics. It has forced us to confront the nature of gravity, space-time, and information in ways unimaginable a century ago. And so we are left with a haunting question. Can an illusion be so powerful that it shapes the universe? If gravity is emergent, if it is born from information rather than fundamental law, then yes, an illusion can hold stars together, guide galaxies, and dictate the fate of black holes. Illusions in physics are not falsehoods, but emergent truths, shadows cast by deeper realities. The information paradox reminds us that even the most overwhelming forces may be masks worn by something subtler. Our journey now turns from the depths of black holes to something closer to home, our own human perception. Gravity feels undeniable. We wake each day to its pull, we move under its weight, we build our world in its grip. How can something so immediate be an illusion? The next chapter will explore why gravity feels so real to us, and how physics teaches that even the most convincing experiences can arise from deeper origins we cannot see. Every theory we have explored so far, from Newton's invisible pull to Einstein's curved spacetime, from holographic projections to entanglement webs, has treated gravity as a concept in physics. Yet long before it was a concept, gravity was an experience. It is the first force we ever feel. As infants, we struggle against it to take our first steps. As adults, we carry its weight in every movement. Gravity defines our sense of up and down, our balance, the strain of lifting, the relief of falling into rest. It is so deeply woven into our lives that imagining its absence is almost impossible. This is what makes the idea of gravity as an illusion so disorienting. Illusions are things we see and later discover to be false. But how can the constant tug of the earth, the tides of the oceans, the orbits of the planets, all be illusions? The key lies in understanding that illusions in physics are not deceptions. They are emergent truths, large-scale realities that arise from deeper causes. Heat is not a substance, but the collective motion of molecules. Pressure is not a force in itself, but the impact of countless collisions. In the same way, gravity may be the emergent truth of space-time, a sensation and a law born from the hidden patterns of quantum information. Our perception of gravity is shaped by the body as much as by the mind. Every cell in our muscles and bones is built to resist the Earth's pull. Our inner ears contain fluid-filled canals that sense acceleration and orientation. They tell us when we are upright, when we are falling, when we are spinning. These senses are so reliable that we rarely question them. Gravity feels absolute because our biology is tuned to its constancy. Remove it, as astronauts experience in orbit, and the body enters confusion. Muscles weaken, bones lose density, balance falters. To us, gravity is not just a law but a condition of life itself. This immediacy makes gravity feel more real than any other force. We do not feel the electromagnetic fields that guide electrons in circuits, nor the strong nuclear force that binds protons in atomic nuclei. We feel gravity in our weight, in our fatigue, in the strain of lifting a stone or climbing a hill. It is invisible, yet ever present, shaping our daily existence. To call it an illusion seems absurd, yet science teaches us that illusions can be powerful, that emergent properties can rule the world as surely as fundamental ones. Consider the tides. To the fisherman, they are as real as the rising Sunday. To the physicist, they are the result of the moon's gravitational pull, stretching the oceans. To the theorist of emergent gravity, they are the projection of information encoded in space-time structure. The tides do not vanish because their cause is deeper than we perceive. They remain real at every level, even if the explanation changes. In this way, gravity as an illusion does not mean gravity does not exist. It means it is not the ultimate layer of reality. Human perception anchors us to the familiar. We trust what we feel, what we see, what resists our muscles. Yet history shows that the senses are only the beginning, not the end, of knowledge. The earth feels still beneath us, yet it spins. The sun feels like it moves across the sky, yet it is we who orbit it. In the same way, gravity feels like a fundamental force, but it may be the shadow of something deeper. Our perception gives us the illusion. Physics reveals the truth. The next part of this chapter will explore how our intuition about gravity has misled us before, and how understanding it as an emergent phenomenon might change the way we view not only the cosmos, but ourselves. Illusions have always been central to the progress of science. They are not lies of nature, but misunderstandings born of human perception. To the ancients, the Earth appeared flat because the horizon hides its curvature. To early astronomers, the sun seemed to circle the Earth because our senses are anchored to the ground we stand on. Even heat, once believed to be a weightless fluid called caloric, was later revealed to be nothing more than the motion of molecules. Each of these illusions was powerful enough to shape civilizations, and each was overturned by deeper insight. Gravity may be the latest in this long tradition, the most convincing illusion of all. Our intuition tells us that weight is a fundamental property. A stone is heavy because heaviness is part of its essence. But Newton showed that weight is not essence, but a result of attraction between masses. Einstein went further, showing that weight is the effect of curved spacetime. If Verlinde and others are correct, we may now face a third revolution. That weight is not even the result of curvature itself, but of information, entropy, and entanglement. What feels to us like heaviness may be the emergent tendency of the universe to maximize disorder, projected into the experience of force. Consider how we perceive motion. When riding in a smoothly moving car, you feel still, yet the scenery slides past. Your senses are fooled because they respond to changes in motion, not motion itself. In the same way, we may be fooled into thinking of gravity as a direct pull, when in fact it is a shadow of hidden processes. The apple does not fall because of an invisible string tugging it to the earth, but because the geometry of space-time, or the deeper logic of information, guides it along a path we interpret as falling. Astronauts provide a living demonstration of gravity's strangeness. In orbit, they feel weightless, floating as though gravity has vanished. Yet gravity has not disappeared. It is what keeps them in orbit around the Earth. Their sensation of weightlessness is an illusion created by free fall. They and their spacecraft are falling together, continuously missing the Earth as they circle it. Their bodies interpret this as the absence of gravity, but in truth, they are bathed in its influence. This simple example shows how perception and reality diverge, even for the most familiar force. The same divergence appears on cosmic scales. We see galaxies bound together, and we imagine that gravity must be a fundamental tether holding them. But perhaps what we are seeing is only the emergent behavior of information, projected into motion and curvature. To us, it feels like a force as real as any touch. To the deeper universe, it may be nothing more than statistics. The illusion remains convincing because it works. Planets orbit, tides rise, stones fall. Illusions in physics are not false, they are effective as truth itself. This recognition does not diminish our experience of gravity, it enriches it. To know that what we feel as weight may be the whisper of quantum entanglement, the echo of entropy, is to see ourselves as part of a grander structure. Every step we take, every fall we suffer, every orbit we observe may be the shadow of hidden rules. We are participants in an illusion so complete that it becomes indistinguishable from reality. The final part of this chapter will explore how embracing gravity as an illusion might change our relationship with the universe, and why illusions in science are often the path to the deepest truths. Illusions in science have always carried a paradoxical weight. They seem to vanish once explained, yet their impact on our lives remains unchanged. Heat did not stop warming us when we discovered it was molecular motion. The Earth did not stop spinning when we realized it had always been moving. Likewise, gravity will not stop pulling at our bodies if it is revealed to be emergent from information. The illusion does not evaporate. It becomes enriched, reframed by a deeper truth. If gravity is emergent, our daily perception of it remains valid. The apple still falls, the tides still rise, our bones still strain under weight. What changes is the story beneath. Instead of imagining a force written into the fabric of reality, we imagine a theater of entanglement and entropy, projecting the experience of weight and pull. Our lives are guided by this projection, as real in practice as any fundamental law. The recognition that it may be emergent does not diminish its reality, but expands it. We see the familiar force as part of a greater whole, connected to quantum processes that span the cosmos. This shift also affects how we view ourselves. If gravity is an illusion, then so too is the stability we take for granted. Our sense of standing on solid ground, of being rooted in place, is not a permanent truth, but the outcome of hidden rules. We are creatures of illusions, adapted to a world where emergent properties feel fundamental. This is not a weakness, but a strength. It allows us to navigate complexity without needing to perceive every hidden layer. Just as our senses edit the flood of sensory data into manageable impressions, our perception of gravity edits the deeper quantum reality into the simple experience of weight and motion. The lesson is humility. Our perceptions are powerful, but incomplete. They show us one level of truth, not the deepest. To accept gravity as an illusion is to accept that human experience, no matter how convincing, is never the final judge of reality. Science teaches us that behind every familiar sensation lies a hidden architecture, and that the universe is always more than it seems. And yet there is beauty in this: the pull we feel when we lift a stone, the strain in our muscles, the weariness at the end of a long climb. All of it may be the whisper of entanglement, the murmur of entropy, the echo of information weaving space-time. To live under gravity is to live inside a cosmic illusion, one so complete that it shapes the stars and the galaxies. Our perception is not wrong, it is a doorway. It opens onto a universe where illusions are truths in disguise. The journey now moves to its final stage. If gravity is an illusion, if it is emergent from information, what does that mean for the future of physics? The next chapter will draw together gravitons, holography, entanglement, and emergent theories, asking where we stand and where we are headed. It will close with the possibility that gravity may be the deepest illusion of all, not a force, but the shadow of quantum information, weaving reality itself. The story of gravity is not finished. For centuries, it has guided us from apples falling in orchards to the dance of galaxies across the cosmos. Newton gave us the law of universal attraction. Einstein reshaped it into the curvature of space-time. And now quantum physics whispers that even this may not be the final word. We stand at a crossroads, looking into a future where gravity might be quantized as gravitons, where it might dissolve into holographic projections, or where it may emerge entirely from entanglement and entropy. This uncertainty is not weakness, but vitality. Science thrives on unanswered questions. Gravity remains the most familiar of forces, and yet the most mysterious. If it is a quantum force, then we must one day detect gravitons, the elusive carriers of curvature, as real as photons and gluons. If it is emergent, then the holographic principle and Verlinde's proposals must prove themselves in the motions of galaxies and the bending of light across billions of light years. If it is woven from entanglement, then the experiments linking tiny masses may one day reveal its hidden structure. In every scenario, the consequences are profound. A graviton discovery would crown the search for a unified quantum field theory. Confirmation of emergent gravity would redefine the meaning of forces and recast the universe as a tapestry of information. Evidence for entanglement, as the builder of space-time, would shift reality itself, teaching us that geometry and distance are not fundamental, but illusions born of quantum links. Even without decisive answers, physics has already changed. The dialogue between relativity and quantum theory has given rise to new mathematics, new experiments, and new philosophies. We are learning to think of space not as a container but as a process, of time not as a flow but as an emergent rhythm, of gravity not as a force but as an effect. These shifts echo through cosmology, particle physics, and philosophy, reshaping our view of existence. The next part of this chapter will explore these possibilities more deeply, asking not only where science may go, but what it means for us to live in a universe where the ground beneath our feet may be an illusion woven by quantum information. The future of gravity may unfold along several paths, each with its own vision of reality. If gravitons exist, then gravity belongs firmly within the quantum world. Detecting them would be a monumental achievement, proving that space-time itself can be quantized. Such a discovery would open the door to unification, the long-sought dream of weaving all forces into a single framework. Just as photons carry light and gluons carry the strong force, gravitons would carry curvature. They would transform gravity from an outsider into a participant in the grand quantum symphony. The task of detection is daunting. Gravitons interact so weakly that a detector the size of a planet might see only a handful in the lifetime of the universe. Still, the pursuit continues, not only through direct detection, but through indirect signatures in cosmic radiation and gravitational waves. If holography prevails, the universe itself will need to be reimagined. The holographic principle suggests that the three-dimensional world we inhabit is a projection of information encoded on lower dimensional surfaces. In this picture, gravity is not fundamental, but an effect of the projection, a shadow cast by quantum information. The mathematics of holography, already successful in certain simplified universes, may one day describe our expanding cosmos. If so, we will learn that our reality is not the whole but only a screen, its depth an emergent illusion. The implications for philosophy and cosmology alike are staggering. Emergent gravity, as proposed by Verlinde and others, offers another road. If gravity arises from entropy, from the statistical behavior of information, then it is as real as heat, but no more fundamental. Galaxies rotate as they do not because of unseen matter, but because of entropy woven into space-time. This theory must still prove itself against the successes of dark matter, yet its appeal lies in its simplicity. It would reduce the puzzle of missing mass to a feature of information rather than an unseen particle. Should it succeed, our picture of the cosmos will shift from one of hidden matter to one of hidden rules. Finally, the entanglement picture suggests that space-time itself is a network of quantum links. Gravity is then not a force, but the geometry of entanglement, the shape created by the structure of information. In this vision, distance is not absolute, but a measure of how entangled two regions are. Black holes, galaxies, even the expansion of the universe become features of this network. If confirmed, this would be the most radical shift of all. We would no longer think of ourselves as moving through space, but as participants in a quantum web whose links define reality. Each path transforms physics, but all share a common theme. Gravity may not be what it seems. Whether quantized, holographic, emergent, or entanglement-based, it is no longer simply a pull between masses or a curve in space-time. It is a clue, a shadow cast by deeper laws. The final part of this chapter will reflect on what this means for science, philosophy, and the human quest for truth. The fate of gravity, whether revealed as fundamental or emergent, will reshape not only physics, but our entire worldview. If it joins the family of quantum forces through the discovery of gravitons, then humanity will have taken one more step toward a unified theory of everything, a vision Einstein himself longed for but never saw completed. If instead gravity proves to be emergent, arising from entropy, holography, or entanglement, then we will face a truth even more profound, that what feels most real in our daily lives is not fundamental at all, but the consequence of hidden rules playing out beneath perception. This recognition does not diminish gravity, it elevates it. Illusions in physics are not deceptions but emergent truths. Heat is no less real because it arises from molecules, nor is pressure less real because it is the collective effect of collisions. In the same way, Gravity will remain the force that guides planets and shapes galaxies, even if it is revealed as the shadow of quantum information. What changes is our place in the story. We are no longer bound only by a pull between masses, but participants in a cosmic web where information weaves the very fabric of reality. The path ahead is uncertain, but uncertainty is the engine of discovery. Laboratories on Earth are testing entanglement between tiny masses. Observatories scan the skies for signatures of holography or emergent behavior. The mathematics of quantum information is rewriting our picture of space and time. Each experiment, each equation, is a step into the unknown, a step toward answering whether gravity is a force or an illusion. For now, we live in mystery, but it is a mystery filled with wonder. To walk, to fall, to feel the weight of our own bodies, these simple acts may be encounters with the deepest secrets of the cosmos. Gravity may be the most convincing illusion ever crafted, one that binds stars, curves light, and shapes the universe itself. Whether it is carried by gravitons, projected holographically, emergent from entropy, or woven from entanglement, it remains the force that defines our existence. Perhaps in the end, gravity is not a force at all, but the shadow of quantum information weaving reality. If so, then every step we take is a step across a tapestry of entanglement, every orbit a dance in the theater of illusion, every fall a glimpse of the deepest truth. The search continues, and in that search lies the beauty of science, the willingness to question even the ground beneath our feet, to ask whether the most familiar of forces is real or whether it is the universe's grandest illusion.